Hello everyone. In this video we are going to talk about Gaussian mixture models or GMM. This is one of the common methods in machine learning, and this is where you try to fit basically a mixture, a combination of several Gaussian likelihood functions to your data, right? So basically you have a Gaussian PDF, probability density function, that is defined by a center, by a covariance matrix that defines its stretch shape, right? The major directions or the unit, the eigenvectors basically, and also the weight of it, which is determined by the number of data it has over the total data that you have. So here I artificially created three sets of data, three sets of Gaussian numbers, and then basically I stack them together to make the mixture, and then apply my Gaussian mixture to it, and then show you the results. So for that you need to bring in from Scikit-Learn the mixture, which has the Gaussian mixture underneath. We need NumPy, and we need the matplotlib. So here I generate 300 data for one of my Gaussian models or Gaussian PDFs, 600 for another one, and again 300 for another one. So I have overall 1200 data, and the weights are, as you can see, 1 to 2 to 1, or 25%, 50%, and 25%. So one of them is a shifted Gaussian, which I create by creating a matrix with 300 data repeated in a pattern of 2. So it's going to be 300 by 2, one for X, one for Y. And they are random numbers coming from a normal distribution. So it's the rand_n command from NumPy. And then to all of them, I add a center. So instead of being centered at origin, I center it at 15 and 30. So I add this constant vector to all of the rows. So this is the shifted Gaussian. The next one is a stretch Gaussian. So again, I create my data like the last time, right? But here I would rotate this. Center is still at origin, but I rotate it by using a matrix product with a matrix A here, which is 0, -0.7, 3.5, and 0.7. And this is going to rotate it for me and stretch it in one direction, and probably stretch or shrink it in another direction. Remember, the standard deviation from this guy is 1. So if you don't do anything, it is going to be like a circle with 1 and 1. But when you apply a matrix, you can stretch or shrink in one direction, the same in the other direction, depending on the eigenvalues of this matrix, and you can rotate it as well. So this is the stretch rotated Gaussian, and then here I have both of them. So first I add a constant vector to my data, so I shift it, and then I would rotate it. Okay, or I can rotate it then shift it. I can do either one, right? So here, for example, I can go ahead and first rotate it, right, like this. So do a NP dot, and you know this is not dot product. NP dot is really a matrix product. So I first what? I first basically apply my matrix product, and then I would add my center. This way the rotation is not going to affect the translation. So here I have a stretch shifted Gaussian, and then I would use the V stack or vertical stack, and I put all of these and stack them below each other. So I have now a giant 1200 by 2 matrix called X train. That is all of my data, and then I'm going to fit a Gaussian mixture model to it. So in order to apply that, we use the mixture.Gaussian mixture, and we need to pass to it the number of components. Here I know ahead of time that it's 3. Not always you know that, so we can change this number and see what the result would be. So here if I exactly do the number of Gaussians that I have, and then for covariance type I use full. And now you might say, what is full? So there are 4 covariance types that you can pass to this command. There is full, which means each component has its own general covariance matrix. Tied means they all share the same general covariance matrix. Then you have diag, which means they own their own covariance matrix, but it's diagonal. Okay, so there is no rotation basically. It's just diagonal, so it's going to be stretch and shrink, or maybe both stretches, but no rotation. And then spherical, which means basically there is only one parameter, right? And that one parameter is going to scale it or shrink it in the same amount in both directions, no rotation, so it's going to be spherical data, or in this case circular data, because it's 2D. If it's 3D, it would be spherical. So this will let the method know that how many parameters for covariance it should find, and here we ask it to find the full, which has 4 parameters basically for each covariance, estimate all of them. So the things that it needs to calculate for me is I have 3 components. Each one has 2 data in the center, X and Y. Then it has 4 numbers for the covariance matrix, and it has a weight. So 7 numbers per each. There are 3 of them, so it has to give me 21 numbers back. And it does once I say classifier.fit, and then I pass my stack via stack data to it. And then I can get my centers by classifier.means underscore. I can get my weights by classifier .weight underscore, and the covariances by classifier.covariances underscore. So I can show you all of those results. And here I'm doing some basically contour plot to show you those results. So before I explain this, let me show you the result, and then we talk more about it. There we go. Okay, so now if you see them side by side, you can see that the location it guessed for me is this one is 0.02 and 0.03. It's almost 0, right? The next one is at 1.5, 10 to the 1, so it's 15, and the other one is 3 or 30, I'm sorry. So one is at 15 and 30, and the other one is at 10 and 17. And are they close to the numbers that I have? You see that the answer is yes. This one that I did not shift was 0, 0. This one was 15, 30. This one was 10 and 17. So you see that it kind of very, very closely could find the centers that I initially passed to my data. It could find them very beautifully. And here are those clusters, by the way, right? Those PDFs. So this is your stretched one, right, at center at 0. This is the one at 15 and 30 that is spherical, and this is the one that has both. So it has a displacement on 10 and 17, and it also has rotation. So my data looks like this. I have 3 sets of data that are not super attached to each other. They are kind of separated, so my guesses are very accurate. Actually, they are very close to initial numbers. If you look at the weights also, right, you see the weight for this one at 0, 0 is 5.5, and for the other 2 are 0.25, and those are coming from here, 300, 600, and 300. So you see the weights are also beautifully calculated, and if you look at the covariance matrices also, they do make sense. For example, let's look at this this one at 15 and 30, the second one. Look at this. What is it? It's 1 and 1, almost 0 and 0, and this is clearly a spherical covariance matrix, and it is a spherical, right, or circular in this case. If you look at these two, they are not spherical, so your off-diagonal numbers are definitely not 0, and you can see them here, right? This is for this big guy here, 11.5 and 2.7, 2.7 and 0.9. And if you calculate the eigenvalues of that and the eigenvalues of this initial matrix, they should be the same. And the same for this one, 0.5, 1, 1, and almost 5. And again, that one and this matrix, they should have the same eigenvalues, okay? So you clearly see that the data that I got do make absolute sense. Now, if I stretch this data, if I stretch the data and bring them closer to each other, so kind of the data are not disjoint clusters like these, right? Then the estimates are not going to be as clean and beautiful like that, because now fitting three clusters, you might have some displacement depending on how close the data are to each other. And all I need to do is change some of these numbers, right? If I change some of these numbers or these locations, then I should be able to what? Bring them closer to each other. So for example, I can bring this guy down, bring that guy down, stretch this one a little bit, and that could get them close to each other. So let's go ahead and do that, see what happens. So for example, instead of 10 and 17, I make this guy 10 and let's say 10, right? So I make this 10 and 10. And that one, instead of having it all the way up at 15 and 30, I make it like to be at 14 and maybe 18 or something like that. So let's bring them closer, see what happens. And I can also stretch out this guy here and see what happens now. There we go. See, now the data start to kind of mix to each other, and now if you look, my centers are not going to be as clean and beautiful as last time, right? If you look at them now, look at the centers. One is at almost 0 and 0. That's not bad. This one is at 14 and 17. This one is at 10 and 9.93, which are not bad still. They are close to these numbers, right? And the reason is the mixing still not big. All I need is to bring these guys a little bit further down. So instead of 10 and 10, I make this guy 8 and 8, and that one bring closer. So let's mess up a little bit more with the data. 8 and 8, and this one probably 12 and 14 or something like that. And now the estimates should get even less accurate. There we go. Now the data are kind of mixing. Now if you look, this center is at 7.96 and 7.8, so it was 8 and 8. So you see now this number is starting to get off a little bit. This one that was almost 0 and 0, now you see is 0.48 and 0.11. Remember here, that number was what? 0.02 and 0.03. Now look at it. You see, it's now what? It is 0.5, negative 0.5, and negative 0.11. So the center is shifting down. And this one that was at 12 and 39.2, it is 12 and 14. So that's not too bad, right? This one is affected more, and the more I mix the data, clearly the more I have the chance of not getting those beautiful numbers, and of course that is obvious. And the worst can happen if you don't have the knowledge of how many clusters to fit, right? So if you say here, instead of 3, if I say just give me 2 now, that is going to be quite a bit different. So here when I fit it, I say the number of components is 2. Let's see what happens now. There we go. You see now, so it kind of fit 1 here and then fit 1 there. Right? Instead of having 3 separate clusters, now it's kind of trying to merge these 2 into 1 and that one into 1. Okay, and of course you're going to get different things, but you see, because these 2 are merged together, so now the weight of that combination is almost the same as this one, 0.5 and 0.5. Right? So you can look at it that way. Now if you say 1, of course it's not going to be any beautiful, right? Because this is clearly does not look like one beautiful Gaussian distribution. So clearly this looks like 3 if you just look at the data, but if you want to say 2, then this is what you will get. Okay, now let me tell you about this contour part, the code for the contour part. So here I'm generating X and Y data, and the limits I chose is based on the contours that I have and the locations of these, so you can modify those numbers. I pass my X and Y data to the mesh grid command, so it gives me 2D data, and then I flatten the data, combine them together by concatenation, transpose it to get my data for the contours XX. Then, in order to get the likelihood function from the train classifier for each data in XX, I use the classifier dot score samples. This is a method that will return what? The log likelihood for each data in X. So I get that, and then since those logs are negative, I use this negative to make them positive. Then I reshape the Z to be in proper dimensions to go along with X and Y, right? This X and Y, the mesh grid ones, with this Z, so I can do my what? My contour plot here. Here I have a scatter plot and I have a contour plot. What did I pass to scatter plot? I pass my X train 0 and 1, I pass my X and Y data to it, and then 0.5 here is the size of those particles. If I use 1, they're going to be much bigger, and they look like bigger filled circles, which does not look too beautiful. So here I reduce the size, so they look more like smaller particles. And for my contour plot, I pass my X, Y, and Z, and then the next thing I need is this log norm. Remember, my contour plot here, the data that I got from these score samples are log likelihood, not regular numbers. They are not in scale, they are not in linear scaling, they are in log scaling. So what I need, as I said in the beginning, you need to bring log norm from matplotlib.colors. You need to bring this guy, and then here, the norm for those contour lines, use a log norm, and the min and the max are 1 and 1.5. So this is 10 to the 0, which is 1, and the next one is 10 to the 1.5. And for my levels, I go from 0 to 1.5 at 10 levels. Okay, so I use levels numpy.log space. Okay, and this is what you get here. Good. So that's my contour plot on the top of the scatter plot, and this is kind of what I expected to get out of the GMM. So this is the code, and you can write it yourself, and you can change anything that you want, and basically see that it gives you everything that you need from the Gaussian mixture models. So hopefully this video was useful to you. I'll see you in the next lecture. Thank you.